Hi everybody, my name is Omar Zaidan. This is the talk that I gave for my PhD dissertation defense at Johns Hopkins University. My thesis was titled Crowdsourcing Annotation for Machine Learning and Natural Language Processing Tasks. I'm going to start by talking about data a little bit. In machine learning, we say that a program learns if its performance improves with experience. And one form of that experience is annotated data. And we've made a lot of use of annotated data in NLP because the statistical approach has proved to be very effective for a variety of tasks, and the training of the systems for those tasks relies heavily on annotated data sometimes. Something that's really nice about this is this more data or better data pattern, which basically means that if you want to improve the performance of your system, you can just add more data to your training set. And so it's fairly typical to see learning curves that look kind of like this, where the performance measured by precision or accuracy improves as you add more data to the training set. Unfortunately, though, there are some limiting factors to the more data or better data pattern, and probably the most significant of those is annotation cost. So the x-axis here, you can think of it as not just being the amount of data, but actually the cost of creating that data, whether it's time or money. Another limiting factor is diminishing returns. So many learning curves actually look something like this, where they basically start to plateau at a certain point, after which adding more data to the training set doesn't help you that much, or maybe doesn't help you at all. And a third limiting factor is not having access to qualified annotators. In NLP applications, some of the annotation tasks might require specific linguistic skills, and you may not have access to annotators who possess those skills. And so what that would mean is that your data collection effort may not even get started. And in this talk, what we'll do is we'll try to overcome these limitations using crowdsourcing. And crowdsourcing, which is, basically outsourcing to the crowd, basically is the idea of taking a task that has been typically performed by a single individual or a small set of people and giving it to a large group of people, giving it to the crowd to have it done in parallel. And in my work, I relied on Amazon's Mechanical Turk service. And Mechanical Turk is a worldwide online marketplace where requesters, such as myself, can create tasks and post them to Mechanical Turk and have them completed by workers from all around the world. In this talk, these will be the annotators completing the tasks for us. And the tasks on Mechanical Turk are usually fairly simple, and people do them for a variety of reasons. Probably the most important one is the fact that they get monetary awards in exchange for completing these tasks. Now, Mechanical Turk does have some mechanisms for encouraging good work and discouraging bad work. So, for example, requesters such as myself, I can look at a worker's history and see how often their prior work was approved or rejected by other requesters. And so there is some incentive for somebody to do good work. And if you get too much negative feedback, as a worker, Amazon actually bans you. So unfortunately, these simple mechanisms are not enough, and further data filtering needs to take place. You need to exercise stronger quality control. And we'll see again and again throughout this talk how we do just that. And I like to think of this talk as being kind of like four different mini talks put together. And I'll use these four different colors to refer to these talks, to these parts throughout the talk. In the first part of the talk, we'll discuss dialectal Arabic. And we will talk about how we can create large data sets to help train systems that specialize on processing the dialectal varieties of Arabic. We'll see how the data could be useful for a number of tasks, and we'll also observe interesting annotator behavior as we analyze the collected data. In the second part of the talk, I'll introduce annotator rationales. Rationales are a richer type of annotation that will aid text classifiers. And we'll see how we can incorporate rationales into two different methods. One is a discriminative method based on support vector machines, and one is a generative approach based on simple log linear models. In the third part of the talk, we'll see how crowdsourcing can help in performing manual evaluation of machine translation systems. We'll design a simple editing task that can help us recreate HTER scores. And then I'll introduce RIPT, which is an evaluation metric that incorporates human judgments as its core's MT output. And by doing so, it makes it suitable for computationally intensive applications such as the MERT phase in MT training. And in the fourth and last part of the talk, I'll discuss what is the most complex annotation task of the talk, which is translation. We will solicit translations from individuals on Mechanical Turk who are not professional translators, and we'll see that by exercising proper quality control, you can achieve translation quality that is comparable to that from professional translators. And we'll see how this is applicable to rare languages such as Urdu and dialectal Arabic. So let's move to the first part of the talk, which deals with dialectal Arabic. And our main motivation here will be our need for data resources that can help us entrain systems specialized in dialectal varieties of Arabic. And our proposal will be to harvest large quantities of reader commentary from the online versions of Arabic newspapers, because that commentary has a healthy mix of both dialectal and standard Arabic. The data that we harvest will be used to create data sets for dialectal identification, dialectal Arabic to English translation, and we'll also design a task to collect word-level annotations of dialect. So let's talk about Gale and Bolt. These are two of DARPA's projects that focus on machine translation. Projects like Gale added a lot of benefit to the research on Arabic machine translation. One issue is that most of that research focused on modern standard Arabic, or MSA for short. MSA is the one form of Arabic that's standardized. It's used in written form in books, magazines, official documents, but it's rarely, if ever, used by the average person on a day-to-day basis in spoken form. On the other hand, DARPA's BOLT project is focusing on spoken, dialectal, and informal language, which is particularly relevant for Arabic, because Arabic has several dialects which are regional variants of Arabic that I'm showing here superimposed on a map of Middle Eastern countries. So this map is showing one breakdown of Arabic dialects into 5 or 6 major groups. Now these different dialects differ from each other in non-trivial ways, and they differ from MSA as well in non-trivial ways. And just to make it kind of clear what I mean when I say dialect, an Arabic dialect does not have standardization. So there is no, for example, Egyptian dictionary. Or any Egyptian dictionary you might find was compiled by a single individual. It's not compiled by a single authoritative, a central authority or anything like that, whereas MSA is. An Arabic dialect is primarily used for spoken communication. You can think of it as being basically the true native languages of people in those countries. And Arabic dialects are usually mutually intelligible, or although not always symmetrically. And they do have significant vocabulary overlap between them and with MSA as well. And you can think of this group of Arabic dialects as being somewhat linguistically equivalent to the group of North Germanic languages. So Swedish, Norwegian, and Danish are 3 separate languages that do have a lot in common with them, a lot of common vocabulary, and they could be mutually intelligible, again, not always symmetric. But we do treat them as separate languages in computational linguistics. And what I'm proposing is that basically we should do the same thing for Arabic dialects. If you train a system for MSA, don't expect that it's going to do so well when given dialectal Arabic input. And I'll illustrate this to you with this example. Here is an Arabic sentence, and this is a sentence that's written in MSA. And I'm showing the transliteration of the sentence as well, because I don't want somebody who can't read Arabic script not to understand the comparison I'm making on this slide. The English equivalent of this sentence is, when will we see this group of criminals undergo trial? So it's a fairly straightforward sentence. It doesn't have any funny things or weird words. Here's another Arabic sentence, but this one is written in Levantine. And Levantine is the Arabic dialect that's spoken in Jordan, Palestine, Syria, and Lebanon. What I want you to notice is that the two Arabic sentences are not exact matches, even though some of the phrases are. So this prepositional phrase, for example, is preserved in both varieties of the sentence. The question keyword, when, there is some overlap, but again, not an exact match. And here the word that talks about undergoing trial, it does have the trilateral root HKM in both varieties. So what I want you to take from this is that there is some overlap. They're certainly not completely disconnected varieties of Arabic, but they're not exact matches of each other. And the differences between them are not trivial. Now, what would happen if you take the MSA sentence and plug it into an Arabic to English machine translation system? This is the output that you get. When will we see this group of offenders subject to a trial? Now I personally would think that criminals is a better word choice than offenders, but hey, this is a really good machine translation output. And if all MT was like this, then basically our job is done. And I'm not going to tell you which MT system this is. I'll just tell you that it's a really good system. It's very highly regarded, and it's a very well-trained system. I'm going to take the same system, and instead of giving it the MSA sentence, I'm going to give it the Levantine sentence, and let's see what output we get. I'm showing word alignments between the source and the target and the output, but I don't think I really need to show the word alignments for many of these words, and it's really obvious what's happening. Basically, the system is unable to recognize some of these words. They're out of vocabulary, and so it's just basically spitting them out as is. It's doing some transliteration, but that's it. That's all it could do. And, that's obviously a problem. And I'm not going to tell you which system this is. Again, it's not that important. I'll just say that this is a really, really well-trained system and very highly regarded. And so even if a state-of-the-art system is unable to deal with dialectal input, the rest of us don't really have much hope. Now, somebody looking at this might say, okay, hold on a second, what's going on here? I mean, MSA and Levantine, they're both Arabic, right? Why can't the system handle Levantine properly if it does well in MSA? And the main problem is that system has never seen Levantine before. There is no dialectal data in its training set. And using this MSA to English system to translate Levantine is almost like using a Spanish to English system to translate Portuguese. If you take this Portuguese sentence and plug it into an English to Spanish system, again, you'll see a lot of words not being recognized. And the behavior here is extremely similar to the behavior we saw in the previous slide. So I would say that it's actually just as unreasonable to translate Levantine or dialectal Arabic with a system trained on MSA-only data. And right, so if we want to fix this, if we want to deal with this kind of input, step number one is we need to get a lot of dialectal Arabic data. And probably the most viable source of dialectal Arabic is the web, because a lot of content there is more individual-driven and much less institutionalized, and so people are more inclined to use dialect in written form, even though that's not what they usually use it for. So you can think of harvesting data from blogs, forums, or even chat transcripts if you can get your hands on them. And what we do is we harvest reader commentary left on the online versions of Arabic newspapers. So this is what I mean. Here's a page. This is an article from an Egyptian newspaper from their website. And the body of the article itself is an MSA, so it's not that interesting for our purposes. What's interesting is if you scroll all the way down to the comments section, you'll see that the reader commentary is actually a mix of both MSA and Egyptian, the local dialect spoken in Egypt. So the first and fourth comments here are in Egyptian, and those two comments are in MSA. What's really interesting is that this fifth one right here, the author starts writing in Egyptian, they switch to MSA, and then they switch back to Egyptian. So there's a really good mix of both varieties here. So we created the AOC dataset, the Arabic Online Commentary dataset, by harvesting this reader commentary from three sources. One was a Jordanian newspaper, where we expect to see a lot of MSA and Levantine, a Saudi newspaper that has a lot of MSA and Gulf, and an Egyptian newspaper that has a lot of MSA and Egyptian. And again, this data has a very healthy mix of dialect and MSA, and even the MSA data is interesting for some research applications because it's an informal variety of MSA. Now, because there is this mix of dialect and MSA, and we're really interested in the dialectal sentences, what we did is we created an annotation task on Mechanical Turk asking people to annotate each sentence with a dialect label so that we can separate the two types of sentences. And the interface looked something like this. So here's an Arabic sentence, and we give them a drop-down menu, and they can tell us how much dialectal content there is. So maybe there's no content whatsoever, or maybe it's entirely dialectal. And if it does have any dialect in it, a second drop-down menu is enabled, and they can tell us, it's in Levantine, or it's in Gulf, or Egyptian. And at the time, we picked a relatively small subset from the AOC of about 100,000 sentences and had them labeled on Mechanical Turk. And at the time, this resulted in Mechanical Turk's largest batch of tasks. We asked for each screen to be completed by 3 different workers. That is, each Arabic sentence had a dialect label on it from 3 different annotators. And the total cost for our data collection effort was about $3,000, which is amazing because we managed to get over 600,000 labels. So that's a really great rate. About 450 annotators participated in the effort, which was really nice because we were not sure how many Arabic speakers there are on Mechanical Turk at first. And our most prolific annotator completed 6,000 of those screens that I showed on the previous slide, even though each one had 12 sentences. So this person did a lot of work for us. And the really good news is that about 40% of the content was labeled as being dialectal. And this is great. Typically, if you look at Arabic datasets from the LDC, they're entirely an MSA, and the dialectal content is only going to be 1 or 2% or not at all. So this is a really good percentage. And if you look at the label distribution if you look at the distribution of the labels that we collected, again, you'll see that maybe about 60% is MSA, and the portion that's been annotated as being dialectal, it's split evenly across the 3 main dialects: Levantine, Gulf, and Egyptian. And if you look at the label distribution for any one source, the distribution is what you would expect. So from the Jordanian newspaper, the predominant dialect is Levantine. In the Saudi newspaper, it's Gulf. And in the Egyptian newspaper, it's Egyptian. And if we look at the label distribution from particular annotators, we'll see some interesting behavior. So the annotators vary in how well they perform this task. Let me take this one annotator. This is their anonymous ID assigned to them by Amazon. And I'm going to look at their label distribution across each one of the 3 news sources. And if we look at their labels on the sentences from the Egyptian newspaper, we'll see that they said, yeah, a lot of these sentences are Egyptian, and they found some Levantine in the Egyptian newspaper. For the Saudi newspaper, they find a lot of Gulf, which is expected, and they find a lot of Levantine. In the Jordanian newspaper, they find pretty much only Levantine. Now, looking at this, I was a little surprised because when I was looking at the data, I did not see much or any Levantine in the Egyptian and Saudi newspaper. Right? But this seems to indicate that speakers of Levantine comment all over the place. And actually what's happening is, that's not actually what's happening, and it turns out that this particular annotator was a speaker of Levantine. And we know this information because we collected from them. We asked them, what is your native Arabic dialect? And if we do the same kind of analysis for a different speaker, who happens to be an Egyptian speaker, we again see this native dialect bias. So yeah, this speaker finds a lot of Egyptian in the sentences from the Egyptian newspaper, but they don't see any Levantine or Gulf. This gray color right here is the general label. We envision this label as a way for annotators to indicate to us that a sentence is obviously dialectal, but there is no reason to classify it as being as in one dialect over another, because remember, there is a lot of overlap in the dialects. What ended up happening is people use the general label to just mean I'm not sure or I don't know, which is very clear in the case of this annotator when we look at their label distribution on sentences from the Jordanian newspaper. So they do correctly identify a lot of Levantine, but for a lot of the other sentences, they just can't really tell what they are. And they do see some Egyptian in these sentences as well, which the Levantine speaker did not. And what's really interesting is when you look at their label distribution on sentences from the Saudi newspaper, because they find almost no Gulf. Now, this is obviously not because there is no Gulf sentences, but probably because this speaker was not exposed to the Gulf dialect, so they're not really able to recognize it. So they're either misidentifying it as Levantine or just saying, oh, this is some just general dialect, I'm not sure what it is. So there is an interesting native dialect bias, and it's even more clear if you look at annotators as groups of speakers. So if you look at the group of all Egyptian speakers, you'll see that they over-identify Egyptian on the sentence that they annotate, and the same is true for Gulf speakers and Levantine speakers. And another variance in how annotators perform this task is their MSA bias. So this is a chart where each data point represents a single annotator. The size of the data point represents how much work they've done for us. So this big circle right here, which is centered over here, represents that most prolific annotator of ours. And the x-axis is their dialect recall. That is, how often were they able to classify a dialectal sentence as being dialectal. And the y-axis is the MSA recall. The first thing to notice is that most annotators are over here, so they have both high dialect recall and high MSA recall. This was a good thing because think of this as a sanity check. If most people are agreeing on this and most of them have high recall rates, this means that the task is making sense to them, and high levels of agreement. That's a good thing. On the other hand, but still, there are some annotators that have either an MSA bias, they over-identify MSA, and so they have a low dialect recall rate, or some of them have a dialect bias. They over-identify dialect, and so they miss a lot of the MSA sentences and have low MSA recall. Now, this is all interesting annotator behavior, but we really care about the data itself. So we have this huge data set of sentences with their dialect labels. And one thing that you can do with these labels is to train classifiers that can distinguish between MSA and the different dialects. And that's something that we did. We trained a number of language models, and that are the basis of text classifiers. And you can get these learning curves. And this is a variety of models. Some of them are word models. Some of them are letter-based models. But they all do fairly well. And the accuracy rates here on this binary task is between 80 and 86%, which is a really good rate. It is especially the rate is especially good when compared to a method that does not use any dialectal data. So the majority class here is MSA, so the baseline is about 60%. And if you look at a method that relies on the gigaword corpus is an MSA, and it basically decides whether a sentence is dialectal or not based on how large the OOV percentage is in, you'll see that method does not do that well. So it does do better than the baseline, but at only 66% accuracy, it's well below all the other methods that use the dialectal data. In fact, even a model based on letter histograms that uses dialectal data does a little better than the MSA method. Let's look at this list of words. This is a list of words from the Jordanian newspaper. So this is in Levantine. And they are ordered by their dialectness factor. And the dialectness factor is basically just a measure of how much more likely a word is to appear in dialectal sentences as opposed to MSA sentences. So words near the top are the most dialectal Levantine words, and words near the bottom are the most MSA words that are unlikely to appear in dialectal context. Now, lists like this one, people have tried to compile them manually. They would, get a number of Arabic speakers, and they would say, "Hey, can you write down for us what you would consider to be the most dialectal words?" And obviously, doing it this way is a much more principled way of doing it because this is based on actual data, and you have this bonus that it's extracted automatically, and that each word actually gets a measure of how dialectal it is. So you can actually quantify it. And when you look at the top words, these are indeed extremely dialectal words. So any speaker of Arabic can tell you right away, yes, these are extremely dialectal words. And it's really nice that we get this dialectness factor that tells us, well, how dialectal it is. And I want you to notice that most of these are function words. And if you look at the bottom of the list, at the most MSA words, you find that they're actually mostly content words. So people seem to revert to MSA when they want to discuss serious topics like politics or religion. Now, what if we do the same kind of analysis on letters? What if we try to identify the most dialectal letters, whatever that means? So here's a chart, here's a figure of the Arabic letters, and on the x-axis is their dialectness factor. Now, I want you to notice that most of them have values that are not that far away from 1, which makes sense. These letters appear almost equally likely in both dialectal and MSA contexts. But there are some differences. There is some variety. What's interesting about this ordering of the letters by the dialectness factor is that the ordering reflects certain dialectal corruptions. So transitions between pairs of letters in red arrows reflect spelling corruptions in Arabic, and Pairs of letters annotated with blue arrows reflect pronunciation corruptions typical of, in this case, the Levantine dialect. What this means, in other words, is if you look at a certain word that means the Jordanian, you're gonna see three different forms of this word, and only one of them is the correct one. It has a correct spelling, and it's the most MSA form of the word. There are two possible spelling corruptions of this word, and we see that if you apply one of those corruptions, the dialectness factor increases, and if you apply the other corruption as well, it increases a little further again. In other words, what this means is that misspelled forms of a word have a higher dialectal factor. In other words, people tend to make more spelling mistakes when they're writing in dialect. Or conversely, they try harder not to make mistakes when they're writing in MSA. This is interesting because it says that people care about spelling more when they're writing in MSA, maybe just because they want to sound smarter or they want to be taken more seriously. And you can see the same thing with these blue corruptions right here. And these blue corruptions correspond to dialectal corruptions of MSA. So this actually, it makes a lot of sense for this word to have a much higher dialectness factor than this version, which is more faithful to the MSA spelling. Another thing that we did with this data was to use it for building a dialectal Arabic to English parallel data set. So you can think of this dialect ID as the first step in a pipeline, in a translation pipeline. So we took these sentences that were annotated as being dialectal, and we passed them on to a translation task. The throughput was a little lower because the task was a bit more complicated, but the quality was really good. And we also added a preferred translator track after identifying certain translators that demonstrated how good they were, and the quality from that track was even better. And some of my collaborators at BBN performed some of their own translation crowdsourcing efforts, and they found that when you train a system on dialectal data, an empty system on dialectal data, it outperforms an MSA trained system by 6 to 7 blue points. Even if that MSA system is trained on 500 times as much data. Another task that we did was to collect sub-sentence annotations. So we ran a task for identifying dialect on the word level. We basically asked people, look at these dialectal sentences and please tell us which part of these sentences make it dialectal, and they can highlight it for us as in these examples. And again, here we see some interesting annotator behaviors because annotators vary in how much content they annotate as being dialectal and how they do it. So most annotators are kind of in the middle here. They have high dialect precision and high dialect recall, but some of them are more liberal in their annotations. So maybe they like to highlight entire phrases or entire sentences. So they have very high dialect recall on the word level, but not that high of a dialect precision. On the other hand, some other annotators are very conservative in their annotation. Maybe they like to pick out specific words, or they have a stricter definition of what makes something a word dialectal. We'll come back to this data that we collected here in the second part of the talk when we talk about annotator rationales. But again, this was just an interesting task that showed us that people vary in how they interpret dialect and deal with it. So to summarize this part, we're motivated by our need for data resources to aid processing of dialectal Arabic. We harvested large amounts of reader commentary from online sources because this commentary has a healthy mix of both dialectal and MSA varieties of Arabic. And we used the data to tackle tasks such as dialect identification and machine translation with a lot of success. Now, in the second part of this talk, I'm going to discuss a new type of annotations called annotator rationales. And the task we'll be interested in here is text classification. And we propose to ask annotators not only to give us class labels, but also why they chose those class labels. This will be a new type of annotations that I call rationales. And these rationales will be utilized by incorporating them into the training of a support vector machine, or by incorporating them into the training of a log linear model. In both cases, we'll see that significant accuracy improvements result, and this improvement is due solely to learning better weights for these classifiers. So what do I mean by richer annotation? Usually we ask the annotator to tell us what the correct answer is. Here I'm proposing that we ask the annotator to also tell us why they chose that answer. And so each training example will consist of information not only about the class but also the reason. So let's take a task of classifying movie reviews into positive and negative examples. So here's a data set of documents. These are movie reviews, and each one of them looks something like this. So this is a movie review written about the movie Saving Private Ryan. Typically, we'd ask an annotator to read these documents and tell us whether it's a positive review or a negative review. In this case, this is a positive review. The author had a positive opinion of the movie. What we're going to ask the annotators to do now is also annotate segments of the text that support the positive classification. These are what we will call annotated rationales. And our annotated data will consist of documents that have both the class labels and these rationales. And you can imagine doing the same thing for a negative review, for example, of this horrible movie. And again, the annotator would highlight segments that support the negative class, and that would be part of the training set. Now, this is nice, but what do you actually do with this kind of data? This is a new type of data, so you can't just throw it at your classifier. And the way we're going to incorporate rationales is by incorporating them into the training of linear classifiers. So in all of the experiments I'm going to show you, I deal only with a linear classifier. It has about 18,000 features. And so you can think of this classifier as just being a weight vector that I call theta, or I call also W at some portions of this talk. Now the rationales will play a role when we learn that weight vector. And the improvements that we get in performance will be due solely to a better learned weight vector. So at test time, there is no change to the decision rule. It's still a linear classifier. There's no change to the features. It's still the same feature set. And most importantly, you don't need the rationales for the test examples. So let's talk about the first method, which is a discriminative method. Let's look at this review again, and let's look at these rationales. Let me ask you this. How sure was the annotator that this is a positive review? Well, they were fairly sure because they highlighted a bunch of those segments. And if you take out one of these segments, they will probably be a bit less sure about their classification. And the intuition here is that we'd like a good model to also be less sure about its classification when one of these rationales is masked out. After all, we are trying to mimic a human annotator. So basically what's happening is we're going to generate these contrast examples by taking an original document and generating a number of contrast examples, each corresponding to masking out one of these rationales, one of these segments highlighted as rationales. So the good model should be less sure of a positive classification on these contrast documents than it is on the original document. And we'll see how we can modify a support vector machine to incorporate this intuition. So the standard SVM tries to maximize the margin between the positive examples and the negative examples. And the way it's done mathematically is by minimizing this objective function right here, subject to a number of constraints that look like this. And what we're going to do is we're also going to incorporate the contrast examples. So these are the blue pluses. And we're going to say not only do we want good separation between the positive examples and the negative examples, we also want good separation between the examples and their contrasts. In other words, we're going to add a new margin that I'm calling mu. And I want to also separate those from each other. Now, I'm not going to get too much into the details about how we do this mathematically. We're still also going to, we basically modify the objective function and we still want to minimize it. What I want you to take out of this slide is that the objective function does not change by much in form. And the form of additional constraints, the additional constraints have the same form as the original constraints. In practice, what this meant is that I didn't have to modify the SVM code at all. I just needed to play around with the input that I gave to it so that it would optimize this problem for me. Now, what this means in practice is that the standard SVM cares about the standard margin right here. Right? It chooses the hyperplane that has maximum separation between the two sets of training examples. On the other hand, the modified SVM cares about two margins, the standard one as well as the margin between original examples and their contrasts. And so it is willing to sacrifice some of the margin for some of the original margin if that means that the other margin will be helped out even by a little bit. right? So it still cares about the standard one. It's not going to do anything too crazy, but it's willing to modify it a little bit if that helps this separation right here. And the main question is, does this do better? Does this generalize better? And the answer is yes. So if you look at this learning curve, this is for the standard SVM that does not use rationales, and you compare it to the modified SVM that does incorporate rationales into its training, you'll see that you get significant improvement in accuracy rates. The second method for incorporating rationales has a more of a generative approach. So let's consider the problem. We have this annotator, right? And they have this really important wisdom and knowledge, and it's basically the weight vector. It's basically theta. And what the annotators do is they use that knowledge to give us the class labels, and then we look at the class labels and try to infer the knowledge back. And the idea here will be that you can do the same thing with rationales. Rationales are based, at least in part, on that knowledge, on that weight vector. So maybe we can use the rationales to infer the weight vector back, just like we did with the class labels. So here's how you would do it with the class labels. The weight vector can be learned by doing something like this. You can maximize the conditional probability of the class labels, right? So basically what you're saying is, I want a weight vector that can model the class labels of the training data well. And one model for this probability is a simple log linear model, right? Now, what I'm suggesting is I'm going to modify the objective a little bit so that not only does it model the class labels well, I also want to model the rationales well. I'm going to add another term to this objective function that says I also want to increase the probability of the rationales. I want the weight vector to explain the rationales in addition to explaining the class labels well. Now, there is no particular model that we have that is that lends itself readily, so let's actually talk about such a model. Let's see what it would look like. And keep in mind, we're looking at this term right here in the objective. We're trying to model the rationales based on the class label, the document itself, and the weight vector. So here's a snippet from a review for Prince of Egypt. This happened to be a positive review. And here are the highlights for two rationales from that snippet. Now, we are going to encode the rationale annotation as a sequence of I and O tags. A word gets an I tag if it appears within a rationale, and an O tag if it appears outside all rationales. So basically what we're going to do is we're going to encode the rationales as a tag sequence, and the model is going to predict that tag sequence with some help from the weight vector. And what we're going to do is we're going to basically use a CRF, just like you would do with things like part of speech tagging or named entity recognition. And so the random variables that represent the tags, we will try to predict them not based on the words themselves, but indirectly through their weights. And this kind of makes sense, right? So if you have a certain word that has a high weight, it's much more likely to be tagged with an I, because it's likely to be a polarized word, and it's likely to appear within a rationale. And how much more likely is that to happen? Well, we learn a parameter, a CRF parameter, phi relevant, from the rationale data that we collected. And this parameter is learned jointly with the weight vector. Now, this is not complete, because what about words like this, like in, and, it's, why were these words given an I tag? It's probably not because they have a high weight vector. There's just a momentum effect happening here. So we add these links as well, and we add 4 additional CRF weights that reflect the likelihood of transitions between the different tags. So just to recap, we will choose a weight vector. It will model all of the data well, both the class labels and the rationales, by maximizing this objective function right here that incorporates terms both for the likelihood of the class labels and the likelihood of the rationale data. The weight vector and the parameters of the CRF are learned jointly, and just to remind you that at test time, we don't change the decision rule. It's still the same. It's still a linear classifier with the same feature set, and we don't need rationales for the test documents. And so the improvements are due solely to a better learned weight vector. And again here, if we do these learning curves, these are the learning curves for the SVM from a few slides ago, and if you add 2 curves for the baseline log linear model and a learning curve for the model that incorporates rationales, again we see significant improvements. And in fact, it does even better than the one with a modified SVM at certain training set sizes. And we do the same thing for the dialect ID task from the first part of the talk. If you remember, we collected word-level annotations of dialect, and we'd see something similar again here. So this is an SVM. This is a log linear baseline. When you incorporate rationales into the training, you get this learning curves, significant accuracy improvements, and the same thing happens with the SVM when you modify it. Now I want to show you an example of a movie review and see how it was misclassified by a standard log linear model, but it was correctly classified by the modified model. This is the bag of words representation of this particular document, and for each word I'm showing it either in red or green to reflect whether its weight was positive or negative, and the size of the word reflects the magnitude. So this says that excellent and memorable were relatively highly positive words, whereas words like director and better were somehow got negative weights. Now this document was incorrectly classified as being negative by the baseline log linear model, and obviously what's happening here is that these words are getting weights assigned to them that are not correct. So there is some overfitting happening here. This was trained on 1,000 documents, 1,000 examples. When you incorporate the rationales into the training, this is what you get. So words like excellent and memorable get boosted up. Words that used to be in red, like director and then, suddenly become neutral, so they have weights that are much more near zero. And so what's happening here is that basically the rationales are acting as a prior on these weights. And we're telling the model that, hey, if this word appears in a rationale, even if you only see it appearing in a rationale maybe just twice, it's okay. You can give it a weight of a high magnitude. And in doing so, it really fixes a lot of the problems with the baseline model. So let me just summarize this part. We introduced this new type of annotations that we call rationales, and we saw how we can aid text classification by incorporating it into the training of two different classifiers. And the nice thing here is that the improvements that we saw were due solely to learning better weights, not because of a more complicated decision rule. So let's move on to the third part of the talk. And here I'm going to talk about how crowdsourcing can help us perform manual evaluation of MT output effectively and efficiently. And the proposal will be that we can use crowdsourcing to collect quality judgments from human annotators. We look at an editing task that would help us recreate HTR scores. And I'll also propose a new evaluation metric that I call RIPT that relies on a database of reusable human judgments. We'll see that the editing task is feasible to perform, but unfortunately it's somewhat challenging to replicate the behavior of a professional editor. On the other hand, RIPT, which was designed with crowdsourcing in mind and is more suitable for a crowdsourced setting, it will end up being a good proxy for a human judgment of translation quality, and it will be feasible to compute it even though it requires a very large number of judgments. So let's start with the HTR metric, human targeted TER. Now TER, as you know, is just a translation edit rate. In other words, you count the number of changes you'd need to make to an empty output, transform it into an existing human translation. And the more changes you need to make, the lower the quality, and the fewer changes you need to make, the better the quality. So TER counts the number of changes you need to make, and human targeted TER counts the minimum number of changes to turn it into some acceptable translation that is not necessarily the same as the pre-existing translation. So you'll see that HTR requires fewer changes in this example. Now, computing HTR requires somebody to perform these edits, which requires you to hire human editors and train them. And so we tried to do this on Mechanical Turk. So we got our hands on some interesting data. We got the final output of one of the teams participating in Gale's Arabic to English evaluation, which was about 2,000 sentences. And we asked Turkers to edit the output and gave them a human reference and said, you should match this reference in meaning, but you should make as few edits as needed. And we also have the edit actions by the professional LDC editor, which will allow us to compare how well the Turkers are doing. The editing interface was pretty straightforward. We pre-populate text fields with the empty output, and we'll also show the annotators the human references that they should try to match. The results are not so great. So I'm showing here a pair of bubble charts, and again here each data point represents a single editor, and the size of the data point represents how much editing they've done for us. What I'm showing here is on the x-axis is the edit rate for the Turker, and on the y-axis is the edit rate of the professional LDC editor. So what you'd like to see in this figure is a lot of data points along the x equals y line. Now you see some of that happening in the broadcast news genre, right? So there is somewhat of a pattern that looks like x equals y. In the conversation genre, though, it does not happen. So, somebody like this, for example, they're doing a lot of editing. They have a 45% edit rate, but the professional editor on those same segments only has about 15%. So this person is doing too much editing. People over here are not doing any editing at all. So there are some problematic behaviors here. And even if you average the edits that you get back, so we ask for each sentence to be edited by 5 different editors, and even if you average the edits that you get back, you still don't get good results. If we try to predict the ranking of the documents from the Turker edits, if you try to replicate the ordering from the professional editor, we don't do so well. And in fact, even automatic metrics like TER and BLEU would do a better job in predicting the ranking. So we said, okay, maybe we can, instead of just taking an average, maybe we can take a weighted average of these edits, and we can weight different editors, depending on how close they are to the professional editor, on a small calibration set. So we take a small subset of the data that we have, and we assume that we do have the gold standard edits for them. And then that enables us to weight each editor depending on how close they are to the professional editor's behavior. And when you take a weighted average, you do a little better. And the larger your calibration set is, the better you do as well. So here are some results. And basically what I want you to take from here is that this baseline right here is the TER baseline. This is how well the TER predicts human editing behavior, the professional editor's behavior. And those two curves are when you take weighted averages from Turkers and based on how much calibration data you use. So obviously the more calibration data you use, the better you'll be able to predict the professional editor's behavior. But in the conversation genre, for example, you need more than 20% of your data for calibration just to even catch up with the TER baseline. So, overall, these experiments told us that the editing task, even though it was feasible to actually perform on Mechanical Turk, the results that we get back wasn't that great, at least according to our measure. It was difficult to replicate the behavior of the LDC editor. And even a second LDC editor would not have predicted the first one's edit actions perfectly. But most critically, minimizing the number of edits was a top priority for the LDC editor, and that was not the case for the crowd apparently, because maybe we didn't emphasize it well enough, or maybe they just did not care about it too much. Now, critically, the LDC editors had a very useful tool at their disposal that actually showed them the number of edits they were making as they were editing the sentences. So that really helped them a lot in minimizing the number of edits as required, whereas the Turkers did not have such a tool. So, this wasn't so great. This editing effort did not turn out to be so great, and we found Mechanical Turk to be useful for something else, which is another metric that I call RIPT, that is more suited for a crowdsourced setting. The main idea of RIPT is to reward syntactic constituents in the source that are aligned to, quote, acceptable substrings in the candidate translation. So what we do is we get a parse tree for the source sentence and align the source words to candidate words and see what fraction of those nodes in the parse tree align to an acceptable translation. And Mechanical Turk is just going to enable us to collect those judgments. So let's look at this example right here. This is a German sentence. This is the source sentence. And this is the empty output that we want to score with RIPT. We parse the source sentence, and for each node in the parse tree, we take the corresponding source substring and the candidate's translation substring and ask, is this an acceptable translation or not? If so, we label this node with yes. If not, we label the node with no. So some of the nodes have yes, some of the nodes have no, and then we just take the ratio of the yes nodes, and that's the RIPT score. So this translation would have a RIPT score of 0.72. Now, is RIPT a good metric? Is it going to be worthwhile? We have to answer two questions. First of all, is it an acceptable metric? I.e., is it a reasonable substitute for human judgment of translation quality? And is RIPT feasible to compute? Because on the previous slide, we saw that you need to collect all these judgments, these yes-no judgments. So we need to show that collecting these judgments could be done efficiently and affordably. We'll answer the first question empirically by showing that RIPT is indeed a good proxy for human judgments. We'll answer this question first, though, and we'll see. I'll discuss a couple of strategies that we have implemented to reduce the number of queries that we need to make, to reduce the number of labels that we need to collect. The first strategy is to reuse the judgments that we collect. So for each source sentence, we build a database, and each entry in this database is a tuple that connects a source substring, a candidate substring, and a judgment, either a yes or a no. So, for example, and then we can use that judgment across other candidates for that source sentence. So, for example, if we had this German sentence right here, and we got a judgment that says that the patient is an appropriate or acceptable translation for this German substring here, I'm not going to try to pronounce it, then we store that judgment in our database, and we reuse it whenever we see that same English substring, even in different candidates. So we don't actually query human annotators for those. We just assume that they're going to tell us the answer is yes, and we reuse this. And you can imagine something very similar if the answer was no. Again, we store this in the database for this source sentence, and we can reuse it across other candidates where the same candidate substring appears. The second strategy that we implemented is label percolation. We can minimize label collection even further if we take these labels that we collect and percolate them through the parse tree. In other words, if a node in the parse tree was already labeled no, the ancestors for that node are probably going to be labeled no as well. So we don't even bother to ask an annotator, and we just percolate the no labels up the tree. And similarly, if a node is labeled yes, it's very likely that its descendants would also be labeled yes if we were to ask an annotator. So we don't ask an annotator and simply percolate the yes labels down the tree. So this also saves us from querying for every single node in the tree. And the way we select which nodes to select is basically kind of to build this frontier node set, in the sense that it covers the source sentence completely, but there is no overlap. So none of these nodes have overlap between them when you project them on the source side. And we make sure that they don't exceed a certain length, max len. For example, this is max len equals 4. And how do we get these labels? We get them from Mechanical Turk. So we designed this annotation task where we show annotators a source sentence and a particular source substring we're interested in, and we show them several possible translations for the substring within the context of several candidate translations, and we ask them, is this an acceptable translation or not? Now, we don't require annotators to understand the source language, which is German in this case, so we do show them a human reference that was provided that exists, and we do highlight within that reference our best guess as to what this word means. We do highlight it in different color just to emphasize that sometimes there could be word alignment errors. Here's another example with somewhat of a longer substring. So again, the source substring, and here's a number of possible translations for it. And we ask them to tell us for each one whether it's acceptable or not. So we did this, and just to summarize, this resulted in about 13,000 queries from the candidate translations taken from nbest lists for 250 source sentences. Now, I want you to think about this number a little bit, because it really means that we only need about 50 queries per source sentence. 50 queries, or 50 yes-no labels, basically, to be able to score all 300 candidates for that source sentences, from that source sentences nbest list. Now, this is really great, because if you think about it, on average, any one of those candidate translations is going to have a parse tree with anywhere between 10 and 20 nodes. And so you would need thousands of labels if you want to get a label explicitly for each node. But using our strategies, we managed to cut that number down to about 50. The effort was gathered over about 31 man hours, which means that each label took about 8 seconds to provide. So we answered this question right here. Yes, it's a feasible metric, and you can collect these judgments fairly quickly. So, is RIPT an acceptable metric? Is it a good substitute for human judgment? And what we're going to do here is we're going to do a little experiment that compares the predictive power of RIPT versus BLEU. we will compare the top one candidate by blue score versus the top one candidate by rift score and ask a human annotator which one of those two is a better translation. So here's basically what we're going to do. We have a list of candidates. This is a list of the n-best list for some source sentence. And we score each one with a rift score. So here candidate number 5 had a high rift score, number 6 not so much. We do the same thing with blue. We compute the blue score for each candidate, and then we pick the highest scoring candidate according to blue and the highest scoring according to rift and compare them to each other. We ask a human judge which one of those two translations is a better translation. We collect 750 judgments, and we see that rift's choice is preferred almost half the time, whereas blue's choice is preferred a little over a third of the time. And when you take a majority vote breakdown, you see something very similar. So for half of the sentences, the majority say that rift's choice is better. And within those votes, majority votes, when rift's choice is preferred, it's usually preferred strongly about half the time, which is a higher percentage than for blue. Now, I was looking at these results, and these are obviously encouraging results, but I was thinking that blue sort of has an inherent advantage here, because the choice, the candidate translation that gets a high blue score, by definition will have high overlap in word choice with the reference translation that we show to the judge. Again, we don't expect people to understand German, so we show them the human reference to enable them to decide which one is the better translation. What that means is that when the annotator is faced with two candidate translations that are of comparable quality, they might go for the blue choice just because it looks artificially closer to the human reference, just because it has some of the same word choices. So what we did is we repeated the same experiment, but we hid the reference. We hid the human reference and just asked people, can you tell us which one of those translations is better, based only on the source sentence. Now, of course, this requires the judge to understand German, so we restricted this task to workers in Germany. Now, here are the results from the previous slide, right? So 46% of the time, rift's choice wins. Under the new setup of the experiment, where there is no human reference, rift's choice is not affected by much, whereas blue's choice loses about 7 percentage points, which means that the two candidates are more comparable to each other than you would otherwise think if you were also shown the human reference, because blue's choice is going to look artificially more like it. So in summary, we saw that crowdsourcing can help us perform manual evaluation of empty output. Manual evaluation, which is usually a lengthy and costly process. You can do it effectively and affordably on Mechanical Turk. We saw how you can perform the editing task on Turk. We found that it was feasible to perform, but the results that we got back were not that good. And we introduced RIPT, which is another empty evaluation metric that is well suited for a crowdsourced setting, and we showed that it's a good proxy for human judgment and feasible to collect judgments for. Now, I'll move on to the fourth part of the talk and the last part of the talk, where I will discuss what is the most complex annotation task of the talk, which is translation. Specifically, we will try to rebuild an Urdu to English parallel data set by collecting translations from individuals on Mechanical Turk who are not professional translators and who are also non-native speakers of English, the target language. Crowdsourcing makes those translators accessible to us, even though they're located mostly in India and Pakistan, where Urdu, the source language, is spoken. Unfortunately, a lot of the translations that we get back are of inferior quality, and we must perform relatively aggressive data filtering. We will discuss a set of features that can help us distinguish good translations from bad translations. And we can see that after you apply this filtering, we achieve translation quality that is comparable to that from professional translators. So this is what a parallel corpus looks like. It's basically a data set that has two sides in two different languages, but preserves the meaning and the content. So this is a very small example of an English-French parallel corpus. And in statistical machine translation, that parallel corpus is very useful because a system can learn by seeing the many translation examples from that data set in form of sentence pairs. And that's really nice because a lot of the engineering that goes into making those systems is independent of the language pair. And again here, more data, better data, so you can usually improve the performance of your system if you just add more sentence pairs to your parallel corpus. What's not so nice about this is that if you don't have a parallel corpus, you can't really do machine translation, at least not any variety that requires statistical learning. So what you would do is, if you don't have such a corpus, is you would create one. You would go to a professional translator, and you would give them a big chunk of text in the source language and tell them and ask them to translate it into the target language. What's good about this is the quality that you get back, you're almost guaranteed that it's going to be very good. What's not so good is that, well, they do get paid to do it, so it's pretty expensive. It's going to take too long. It might take weeks or even months to complete this. And it may not be possible for some rare languages. You may not be able to find translation agencies that can handle certain languages. So, given the topic of this talk, we asked, what if we can crowdsource the translation task? And this would actually take care of a lot of the problems with professional translation. So, crowdsourcing translation makes it not as expensive. It's not going to take as long because you have a lot of people working on it. And it might actually give you access to people in international markets that you didn't have access to before easily, and you would be able to translate more languages. But one problem with crowdsourcing translation, which is actually a big problem, is that of quality. So the quality that you get from crowdsourced translations is not always great, and if the quality is not so good in your parallel corpus, you can't count on the quality of your empty system, which is trained on that corpus. Now, let's look at a case of Urdu. And let's look at the case of Urdu to English translation. Now, Urdu is a relatively rare language in terms of the available resources, but it's spoken by tens of millions of people in countries like India and Pakistan. If you look at the data available for Urdu and compare it to that available for other languages, you'll see that it's actually a very small amount of data. So compared to the Europarl corpus, which allows you to train empty systems for European language pairs, or for the data made available for the Gale teams for Chinese and Arabic translation. So you can see that there's very, very little resources available for Urdu, and it was designated by the LDC as a less commonly taught language. This is a list of languages that includes Bengali and Hungarian. These are languages that are spoken by large numbers of people, but for which we don't have a lot of resources. One resource that we do have is this data set created by NIST for their annual evaluation. They did it by taking a set of about 1,800 Urdu sentences, and they created 4 sets of reference translations for them. So for each source sentence, we had 4 reference translations. Now, the quality here is really good because they got this from a professional translator. And not only that, but this multiple reference data set is useful for us. It's useful for research because we can see how close the professional translators are to each other. Okay, so what we did is we took this NIST data set and we retranslated it on Mechanical Turk. This allows us to evaluate the quality of the translations we get back in an objective manner. And we also have an idea of what a realistic goal could be. By comparing the different professional translators to each other, that gives us a realistic goal to aim for in terms of the quality we get by crowdsourcing. So this is our interface for translation. We give them the Urdu sentences and ask them to provide the English translations in these field boxes. We also ask them some information about themselves, such as what is your native language, how long have you spoken Urdu, because this is helpful information. We paid $1 for each group, for each screen, which had 10 sentences on it, and we had each sentence done redundantly. So we ended up with 4 crowdsourced translation per source sentence. Almost all of the workers were located in Pakistan and India, and they identified themselves as being native speakers of Urdu, but non-native speakers of English, even though English is the language in which they're composing sentences. And let's look at these translations. And here are the Urdu sentences again. And here are the translations that we got from Mechanical Turk. So, this is okay. 140 years old, 9 kilo, waiting, lobster free. Not too bad. Maybe not as good as the professional translation, but not bad.
This is not a good translation, right? 140 years ago, 9 kilogram lobster was free. Absolutely not what the sentence was saying. Here's another one that's not good at all. Lobster. This is just a naive transliteration of the word in Urdu. And again, George instead of George. This person is obviously having difficulty composing English sentences that are correct. But here's a set of reference translations that are actually pretty good. 140-year-old, 9 kilo lobster free. That's actually pretty good. They're good with capitalization. So there are some good translations. There are some translations that are not so good. Some of the translations are pretty horrible. A lot of the translations are actually spammy. And in fact, on our first collection effort, we only collected a single translation for each source sentence, and that just looked really bad. And we basically suspect that a lot of Turkers, they would copy and paste the text, the Urdu text, into an empty system and just give us the output back. So in our later collection effort, we converted the text into images first. And there we collected 3 translations per source sentence, and that's how we got 4 translations per source sentence. We didn't throw out the data from the first collection effort, but they are not as good. So we did end up with 4 translations per source sentence. Now, let's look at the big picture here. Let's take a step back and let's move away from the crowdsourced translations first. Let's look at the references, the professionally produced translations. What I'm showing here is a blue score for each one of the reference set, and this blue score is computed against the other references. So this gives us an idea of what the blue score range is for reasonable translations. And I'll just say that for reference set number 4 in particular, it looks slower. It looks lower, and when I looked at the data, it's not because it's bad data. They just had a very different style of translating from Urdu to English. But this is good translation. So this really tells us that there's kind of a range of values that would be acceptable. If you compare this to the data we get from Mechanical Turk, the numbers are not so good, right? So here's that one batch that we did at first. Really low score. This was really bad quality control. And here are the other 3, better, but still not that good. So they don't even go above 30 blue points. And just to kind of make it clear how bad this is, if you take the output of empty systems, the difference is not that big. So this score is by taking the output of a state-of-the-art Urdu to English empty system, and compared to Turkers, it's not that much worse. It's not that much worse. So it's obviously these translations are obviously problematic. I'm going to condense this chart a little bit. I'm basically going to take I'm going to take these 4 numbers and kind of average them and do the same thing for the Turkers. And this is what you get. So this is the average score for references. And I'm keeping these red lines, these are the original values, and I just want to keep them as a reminder that there is some variation. They're not like all within just around the 41 mark. And so, our goal will be this gap right here between Turkers and references. We'd like to overcome it as much as we can. Now, before we try to filter that data, I looked at a couple of Oracle scenarios. And I said, is there any good at all? I mean, is there something good in there? And the answer was yes. So if you look at a segment-level Oracle scenario whereby out of the 4 crowdsourced translation, we pick the one translation that is closest to the references, you get a blue score of about 44, which is really good. It's within the range of professional translations. And even if you do the Oracle scenario on the Turker level, you're still going to do really well. Now, what this says is that there's almost always at least one good translation. And it's important to keep in mind here that this Oracle scenario is actually pretty realistic because you're choosing one out of only 4 translations. This is as opposed to Oracle scenarios where you're dealing with n-best lists of 300 or 1,000 or even a lattice that's encoding thousands or millions of translations. So this is actually a realistic goal, trying to match the Oracle scenario, right? And the goal will be here to identify the good translations from the bad ones. And I'm going to basically be filling up the rest of this chart with numbers that show you how well you do based on when you use these filtering methods. So let's talk about how we can filter this data. Now, let's say I give you this task, and I want you to tell me out of the 4 translations that I got from Mechanical Turk, which one is the best one? How would you do this? What does a good translation look like? And I want to assume that you don't understand Urdu. Well, one thing you would do is you will just look at the sentences and say, well, I'm thinking that if a translation looks like good English, then it's probably a good translation, right? So this is a property of the English translation without even looking at the source. So here are the 4 translations that we collected for this particular source sentence. I don't understand Urdu, so I can't read this. I don't know what it says. But I'm willing to bet that the translation from the first Turker is not a good translation. Make us aware about your opinion. I'm pretty sure that the professional translations do not look like this. And the same for Turker number 4. Do enlighten us with your views. Again, I don't think that's how a professional translator would write this, would translate the sentence, because this is not particularly natural English. Turker number 2 and 3, on the other hand, please give us your opinion. That's more natural English. So that's likely to be a better translation. Another thing that you see between for Turkers 2 and 3 is that they basically give the same translation. And a translation that has consensus is probably also a good translation. So here's another example for consensus. Again, I don't understand the Urdu sentence, but I'm willing to bet that Turker number 2 and 3 are probably getting it right, just because they happen to agree. And people are much more likely to agree on the correct answer than they are on the incorrect answer, because there are many more ways to answer incorrectly. So we basically compile a list of features. These are just properties of the English sentence that would give you a clue as to whether it's a good translation or not. So we look at the language model score, we look at the length of the sentence. This eliminates really short ones and really long ones. We look at the percentage of OOV engrams, so sentences that have a higher OOV occurrence, it's probably not good English. We also look at the added distance of any translation compared to the other translations. So a translation that has low average added distance is probably a consensus building translation, and it's probably a good one. And we just pick the translation that looks best according to these features. And if you do that, you get a blue score of about 32 points. Now, this is a crude weighting of these sentence. These are sentence features, and they have very crude weights. If you use a small set of the gold standard translations, about 10% of the data, to tune these the weights for these features, you get a further boost, which makes sense, right? Because these features have they differ in the magnitude, and they differ in how predictive they are, and so you really ought to tune the weights for them. Now you can already see that we're kind of bridging that gap, so we go from 28 to 35 just by looking at the how good was the English in those translations. So what other things can you do? So this is the same task. I want you to pick the best translation. We just saw a number of features of the string itself, the English string. But what about the Turker? If there's a translation that doesn't look that good based on the sentence features, but it comes from a Turker that we know does good work, then maybe we should tolerate that translation. And vice versa, if a good translation comes from a not so good Turker, maybe good translation in terms of the sentence features, maybe we should be a little suspicious of it. Now, what makes the Turker good or bad? The same things that we were just discussing, but aggregated on all of that Turker's submissions. So we look at features like the Turker's language model score over all that Turker's translations. And the same thing for all these other sentence features, just aggregated on the Turker level. There are other properties of the Turker that we can look at, such as their location, their knowledge of the two languages, and how much time they spent on the translation. So if they're not spending much time on the translation, it probably means they're not doing a very good job. And if you use these Turker level features, again, you see this boost from 28 to 36 blue points. So it's really a good idea to give good Turkers the benefit of the doubt, even if some of their translations have not so good sentence level features. Now, one thing that you can do is you can crowdsource the quality control procedure. So we're going to do Mechanical Turk crowdsourcing quality control using Mechanical Turk. We're going to take these translations, and we're going to ask Turkers located in the United States to tell us which one is the best one. So these are going to be likely native speakers of English. So they're going to tell us what they think is the best without really looking at the source, because they wouldn't really understand Urdu. or at least not many of them would. And if you only look at these, if you look at the answers that we get back by ranking, again, you see a really big boost. Now, so far we've been tuning the weights for these features using a small calibration set, right? So we've used a small data set to set the weights for the features that we extracted. But we can use that data set to compute other certain useful features. And in particular, we're going to measure how close a translator is to the gold standard translations. And we will use that that score, if you will, I call it the calibration feature, to select the best Turker, the translation from the best Turker. And again, you see this boost going up to about 38 blue points if you use the calibration features on 10% of the gold standard data. If you use more gold standard data for the calibration, you get further improvements, but we want to look at only the 10% scenario because that's a more realistic scenario. You wouldn't probably have that much gold standard data to begin with. And if you put in all the features together, you get a further boost, and you get to about 39 blue points. Now, notice that by then you're already in the range of professional translators, and this is great, right? This says that you take the crowdsourced translations that are not doing so well, you apply these filters, and so all of a sudden you're producing translations that are of comparable quality from professional translators. So the big picture here is, do we approach quality professional translation? Yes, we do. And if you're not yet sold just based on these results, I'll tell you that the total time it took us to collect translations was less than a month. The total cost was about $1,500, and compare this to a professional quote, which of about $12,000. So that's an order of magnitude. And if we want to build something for Urdu that's on the order of Europarl, so tens of millions of words, we should really consider the crowdsourcing because we may not want to spend $5 million. It's a really attractive option to spend an order of magnitude less. And there are some experiments that we did on dialectal Arabic. We collected translations for dialectal Arabic into English, and my collaborators at BBN found that they actually collected the data using some of our methodology, and they found that a system trained on dialectal data does between 6 and 7 blue points better than a system trained on MSA data, even when that MSA trained system is trained on 500 times as much data. So it's really important to collect this data, and you can collect the data and you can get good quality data and train your systems on it. So just to recap this part, we recreated a parallel data set for Urdu to English, and even though a lot of the translations that we got were of somewhat inferior quality, we designed a set of features that could distinguish the good from the bad, and we achieved near professional translation quality by applying our filtering strategy. So this concludes the talk, and I'm just going to finish off with a bit of a summary. So we explored crowdsourcing as an option to collect data for a number of NLP applications. And the annotation tasks that we considered form a spectrum in terms of their complexity. They range from the very simple labeling task all the way up to a more complex task that requires annotators to compose entire sentences. We propose new types of tasks, new types of data, and even new algorithms to deal with this data. And I would say that we also looked at new types of annotators that we did not have access to before for some of these annotation tasks. And one common theme that kept showing up again and again was quality control. It is critical to do intelligent quality control when you're dealing with crowdsourced data. Otherwise, you might get data that is of questionable quality. Here's a quick list of publications that are relevant to what I discussed in the talk. So the first 2 papers cover the work on rationales. The following 2 papers cover the work on performing empty evaluation and manual empty evaluation. This paper right here and the last one cover the work on dialect Arabic identification, and those 2 papers are concerned with crowdsourcing translation. This one is for Urdu, and this one, the main authors are from BBN, looks at dialectal Arabic into English. And I just want to finish off by thanking some people who made this work possible, whether it was funding or my thesis committee, my collaborators, my family, and and my awesome friend Yuri Kinigovich. And thank you also for watching this talk. And I know that I was going through some of these slides pretty quickly, and I was rushing through some of them. Feel more than free to contact me if you have any questions about any of my work. Thanks.